Hi, my name is Vinay Kamidi. Today I would like to present our recent work, Decentralized Control Schemes for Stable Quadrupedal Locomotion, a decomposition approach from centralized controllers. This work is done in collaboration with Abhishek Pandala and Dr. Kavya Akbari Hamed here at Virginia Tech. We propose a decomposition approach based on hybrid zero dynamics, nonlinear control, and quadratic programming towards synthesis of decentralized controllers, also known as local controllers for legged locomotion. This approach evolves local controllers from already existing centralized controllers by considering the strong nonlinear interaction forces between the subsystems and only requiring minimal information sharing amongst these subsystems. We develop exponentially stabilizing decentralized controllers. Our motivation spurs from the performance of hybrid zero dynamic framework over the recent years. It has been employed to control various periodicates ranging from 2D and 3D bipedal robots to lower extremity prostheses and exoskeletons. This framework is preferred because it is known to handle underactuated models. However, despite their superior performance and ubiquitous usage, their implementation is not scalable to higher degree of freedom systems. This is partly due to the centralized approach adopted towards this problem. By considering the entire system as one, the implementation of HZD schemes on high degrees of freedom systems necessitate high throughput computation networks. In particular, HZD schemes require the inversion of a state-dependent coupling matrix to obtain the control law. This poses two major problems. First, the computational complexity of matrix inversion scales as cube of the number of degrees of freedom. Second, the inversion operation amplifies and distributes any modeling errors across the entire full-order model. These problems can be alleviated by decentralization schemes due to the fact that they usually approach the problem by considering that the system is made up of two or more individual subsystems, thereby reducing the number of accountable degrees of freedom locally. The examples of decentralization are shown in the picture to the left. However, decentralization is riddled with its own challenges. To begin with, existing literature on decentralization focuses on the stabilization of equilibrium points of ODEs, but not periodic orbits of hybrid dynamical systems. Furthermore, this breakup into two or more systems brings with them the strong nonlinear interactions that cannot be neglected. Then there is the problem of underactuation and hybrid nature of state-space dynamics. We introduce an alternative approach, a decomposition approach, to tackle the challenges of synthesizing decentralized controllers. This approach assumes the existence of exponentially stabilized orbits by centralized controllers. With this assumption, we eliminate the need to set up large-scale optimization problems for tuning controller parameters, which would have been necessary if we were to consider the general decentralization approach of synthesizing controllers from scratch. Furthermore, we will show that we can achieve exponentially stabilizing decentralized controllers for a quadrupedal robot as shown in the animation below without the need of any communication between the subsystems. In this work, we consider full-order dynamical model of an 18 degree of freedom quadrupedal robot Vision 60. We refer to the four legs moving anti-clockwise starting from left front as leg 0, leg 1, leg 2, and leg 3. We attach a base frame B to the geometric center of the robot. This provides us with 6 degrees of freedom attributed to the global position PB and orientation psi B, and are together encoded in theta. Each leg has 3 degrees of freedom. 2 degrees of freedom are associated with the hip pitch and hip roll. The remaining 1 degree of freedom is allocated for controlling the knee pitch. For a total of 4 legs, we have 12 actuators, and all 18 degrees of freedom are now accounted for. Finally, the state variables are denoted by X. Before we move ahead, let's go over some terminology to capture the hybrid nature of locomotion. In that interest, we introduce the following tuple sigma. Here, G denotes the directed cycle corresponding to the desired gate pattern with a set of vertices V and edges E. D represents the set of admissible domains. S denotes a set of switching manifolds on which discrete time transitions occur. Delta is the set of discrete time transitions, and finally, Fg represents the set of input-affine control laws on domain D. We now address continuous time models of a centralized system. Within each admissible domain, the state of the robot evolves as described by equation 1. Here, D represents the mass inertia matrix. H is the compact notation for the sum of centrifugal, Coriolis, and gravitational terms. B is the input distribution matrix, and lambda is the ground reaction force. Equation 2 represents the ground contact constraints within each admissible domain, where JV is the contact Jacobian. In a similar manner, we can address discrete time models of locomotion, which are triggered every time the robot initiates or breaks contact with the environment. We note that whenever the robot breaks contact with the environment, the state space remains unchanged and is taken as the identity map shown in equation 3. On the contrary, contact initiation is modeled as an instantaneous impact. This is cumulatively described by equation 4 and equation 5. Here the subscripts plus and minus represent variables before and after contact initiation respectively. Assuming that there is a periodic orbit or a gate, we can now develop time-varying centralized virtual constraint controllers to stabilize this dynamic gate of the quadruped system sigma. Virtual constraints are a set of kinematic constraints that are zeroed via feedback control laws to coordinate the motion of the links. In our work, we parameterize the virtual constraints with only holonomic components and is noted in equation 6. Here, H subscript V superscript D denotes the desired variables, wherein tau represents the gate timing variable which evolves according to the following laws denoted in equation 7. Differentiating the virtual constraints in equation 6 along the nonlinear dynamic system yields equation 8, where Kp and Kd are positive definite gains. From the output dynamics, one can now solve for the nominal state feedback as in equation 9. That will result in asymptotic output tracking. However, this does not guarantee feasible bounded torques. We therefore synthesize the control law alternatively by setting up a QP formulation. Here, a slack variable delta is used to ensure QP feasibility. We are now in a position to present the decomposition approach. To make my case, I will take the help of front-hind decomposition. First, we will proceed with the state decomposition. Recall that Q is a 18 by 1 vector of global variables and local shaping variables, which will now be split into QF and QH, where the subscripts F and H correspond to front and hind respectively. Both QF and QH have access to the global variables theta and are further augmented by the actuator variables corresponding to the respective subsystem. Take for example the front subsystem. It has 6 actuator variables that are now added to QF. This makes both QF and QH a 12 by 1 vector. Also note that the control vector is correspondingly split into UF and UH. We will now proceed to decompose the dynamics. We will rewrite the continuous dynamics that were unfolded earlier in the centralized discussion as in equation 10. And noting that Q is now comprised of QH and QF, we will proceed to decompose equation 10. Let's focus in on the front subsystem. On decomposition, we can rewrite the dynamics as in equation 11. Note that earlier we said strong nonlinear interaction forces are manifested by the dormant subsystem, which here is the hind subsystem, onto the dynamics of subsystem under consideration, which here is front subsystem. The manifestations can be seen in the form of QH double dot and UH. Since we are interested in solving for the control vector UF, we make the assumption that UH and QH double dot are on the orbit and hence are aptly denoted by the stars in the superscripts. The vice versa is true when solving for the dynamics of the hind subsystem. Similarly, we can decompose the time-varying centralized control laws into local decentralized control laws. 2 separate virtual constraints arise for each subsystem, and again they do not guarantee feasible torques, and hence we introduce local QPs to address this issue. In conclusion, we now have 2 local decentralized control laws. To numerically evaluate the power of proposed algorithm, we consider a walking gate with 8 continuous time domains with a speed of 0.15 meters per second. The gate is optimized via the use of direct collocation that is formulated as an NLP in Frost. By conforming to the natural symmetries, we choose 3 decomposition schemes to test the performance of the proposed decentralized controllers. These are namely front-hind decomposition, left-right decomposition as illustrated, and finally diagonal decomposition. The illustration of the diagonal decomposition is painful. However, it is easy to visualize. We combine the diagonally opposite legs into pairs and form two subsystems. Furthermore, we evaluate these three decomposition schemes on two gates, a forward walking gate and an in-place gate for thorough numerical evaluation. We simulate the robot for 35 steps. First, we present the results for the centralized controller. Here we observe that both the forward walking gate and in-place gate are stable. It can be clearly seen that the controller converges to an orbit in the phase portraits to the right. Furthermore, the output graph shows that all virtual constraints are asymptotically driven to zero. Similarly, for the case of front-hind decomposition, we can see that with the help of decentralized controllers, convergence to an orbit is clearly illustrated on the phase portraits provided to the right. Here again, we can observe that all the virtual constraints are asymptotically driven to zero. Now we move on to the results of the left-right decomposition. Here again we report that forward and in-place gates are stabilized by observing the convergence to an orbit in the phase portraits provided. Again, the virtual constraints are asymptotically driven to zero. Finally, we present the numerical simulation results for the diagonal decomposition scheme. With reference to the phase portraits provided to the right, we can see convergence to an orbit clearly. Furthermore, the virtual constraints are asymptotically driven to zero. We report that both in-place and forward walking gates are stable. Additionally, we evaluate the robustness of the proposed decomposition schemes by applying a persistent force of 250 newtons throughout the 35 steps taken by the robot for all three decomposition schemes and two different walking patterns considered. The animations are compactly captured in the table shown. The animation shows foot trajectories and is color-coded to denominate the decomposition scheme used. First, for the front-hind decomposition scheme, we can see that both forward walking and in-place gates are stable. A clear convergence to the orbit is observed in the pitch phase portrait for the forward walking gate. Next, in the left-right decomposition scheme, we again see that both forward walking and in-place gates are stable. And again a clear convergence to orbit is visible in the pitch phase portrait of the forward walking gate. Finally, we observe the diagonal decomposition scheme. Here, the forward walking gate is stable and convergence to an orbit in the pitch phase portrait confirms that. However, for the in-place gate under diagonal decomposition scheme, we observe that the gate is not stable. In conclusion, we have developed decomposition schemes to aid in the synthesis of decentralized control laws for quadrupedal locomotion. We have shown that this results in the minimization of the problem's dimension. Additionally, we demonstrated that there is no need for any communication between the subsystems for successful decentralization schemes in symmetric systems. Finally, the strength of the proposed law is demonstrated through rigorous numerical simulations and robustness analysis for three decomposition schemes and two different gates. For future work, we will extend these decomposition schemes to address each leg as its own subsystem. We look to investigate the expansion of the formulation to asymmetric systems as well. Furthermore, we will evaluate the generalized decentralized control laws on an already existing quadrupedal platform, Vision 60. With this, I would like to take the time to thank our sponsors, the National Science Foundation, and the audience for their attention. Thank you.